Physics just confirmed the universe is cheap, the cosmic energy lie. You think reality's infinite, smooth space, endless detail, perfect resolution. It is. Physics says the universe runs cheap, hard caps, speed limits, and an irreducible hiss that never goes away. Here's the simple truth. Energy and information are the same currency, and nature spends it sparingly. I'll show you the receipts, Shannon's bits, Landauer's heat bill from the 196s, Bekenstein's area limit from the 197s, and a test that could break this story. If reality is optimized, your senses are compression artifacts. To see the lie, we start where energy meets information and watch the ledger snap into focus. Energy is information. Shannon, Landauer, Bekenstein. Okay, so basically, if information has a physical cost, then perfect precision is never free. Claude Shannon, working at Bell Labs in the late 194s, gave us the math of information, bits as choices, entropy as uncertainty, and channel capacity as the maximum choices per second you can reliably send through a noisy pipe. That was the blueprint. But the moment you ask, what does 1 bit cost in the real world? You slam into heat. Enter Rolf Landauer at IBM in 1961. Landauer's principle says erasing 1 bit, forcing this, not that, dissipates at least kT ln2 of heat at temperature T at room temperature. That floor is about 2.8 to 3 times 1021 joules per erased bit. Tiny, but crucially not 0. 0 would be the only number that makes infinite precision free. This is the receipt computers can't dodge, and neither can measurements, memories, or any physical process that overwrites alternatives with a definite outcome. Think of it like a pay-per-bit universe. Every time a system commits to yes over no, some energy is pushed into the environment as heat. No free deletes, no perfect resets. If you wanted flawless fidelity everywhere forever, you'd need infinite energy into an infinite heat sink. That's not physics, that's fantasy. Here's the weird part. We talk about computation as something laptops do, not what the universe does. But measurements, memories, and state updates are logical operations with thermodynamic footprints. Maxwell's demon, the mythical cheater of the second law, gets caught at the memory line. To erase its notes, it pays Landauer's bill. Nature's accounting is boringly consistent. Now zoom out. Jacob Bekenstein in the early 197s asked how much information fits in a region before gravity answers no. His bound says the maximum information scales with the area of the boundary, not the volume, for given energy. Push beyond that, and the region collapses into a black hole. The Bekenstein-Hawking area law then says a black hole's entropy equals its horizon area divided by 4gh stroke. Translation: the most data you can store is written on the surface in Planck-sized pixels. Area, not volume. That's compression logic at cosmic scale. Everything clicked when I stacked them. Shannon tells you what bits mean for uncertainty and communication. Landauer sets the energy cost to commit or erase a bit. Bekenstein caps how many bits fit in a region for a given energy and size. Together they scream, detail is rationed. There's a spend to decide, a ceiling to store, a bandwidth to send. Let's make it concrete. Try to describe a tiny cube of space to absurd precision, every field value with infinite decimals. Shannon says that's a huge information payload. Landauer says committing those digits costs heat per bit. Bekenstein says before you're done, gravity collapses your cube. Infinite detail either cooks your lab or makes a black hole. Precision is a luxury. Okay, so what this actually means is straightforward. Computation equals heat. Memory equals mass, energy, and area. Communication equals energy transport. If you want reliability, you add redundancy, more bits, which increases storage demand and energy cost. A universe that wants to run fast and not implode learns to be thrifty. Compress what's predictable, defer decisions until necessary, and only pay for precision where outcomes hinge on it. Wait, what does this show up outside thought experiments? Absolutely. Your phone throttles because compute makes heat. Your brain forgets because retention costs. Your best detectors hit quantum and thermal floors because extracting certainty costs. The confusion we inherit, that nature should reveal infinite detail on demand, dies when you accept that bits have bills. Credibility markers. Here's the lineage. Shannon's 1948 mathematical theory of communication defines bits and capacity. Landauer's 1961 IBM memo, later formalized, sets the thermodynamic cost of erasure. Experiments since the 200s have measured it near the KT-ln2 limit. Bekenstein's 1973 bound, sharpened with Hawking's 1974 radiation result, ties information to geometry. These aren't edgy takes, they're pillars. Micro story. I once explained Landauer with a recycle bin. A friend said, "Can't we just overwrite without erasing?" I said, "If you don't know the old state, overwriting is erasing. If you do know it, you paid to know." She paused. "So there's always a receipt." Exactly. Heat, measurement effort, or gravitational constraint, the ledger always closes. Holographic hints reinforce the thrift. If black holes encode microstates on surfaces, not volumes, nature's most extreme data vaults already run area-based storage. That's not mysticism, it's economy. It's cheaper to store rules on a boundary and generate interiors than to track every interior pixel. Noether's theorem, symmetry implies conservation. We'll tighten this compression story next, but the moral's already clear. Key takeaway for you: if information costs, precision is a budget choice. The universe spends bits where they buy stability, function, and predictability, and compresses everything else. Now, if there's a cost to deciding and a cap to storing, what about speed? How fast can the universe even update? That's where the next constraint bites hard. The speed limit as a budget rule. See Margolus-Levitin. If bits have bills, there's a second constraint that hurts just as much: how fast you're allowed to spend. Everything clicked for me when I realized the speed of light isn't just a trivia fact about photons. It's a budget rule for causality. And quantum mechanics piles on with a separate cap. Even with energy in your pocket, there's a maximum rate at which a system can switch between distinguishable states. Throughput and latency, both capped. Okay, so basically, two constants govern the ledger. First, C sets the maximum reach of influence per unit time. No update can propagate faster. Second, the Margolus-Levitin bound sets the local clock rate. With average energy E above your ground state, you can do at most 2 EH distinct state flips per second. More energy, faster ticks. Less energy, slower ticks. No amount of cleverness turns 1 joule into infinite operations. Think of a simple micro example. 1 joule isn't much. You burn it walking a few stairs. The Margolus-Levitin number says that buys you on the order of 3 × 10^33 elementary operations per second. Huge, yes, but crucially finite. Now spread those operations over a large region you want to keep exquisitely up to date. The number of degrees of freedom balloons, your precise update budget plummets, and C prevents you from instantaneously coordinating distant parts. Result, you can't run the universe at infinite frame rate everywhere. You triage. Here's the weird part. We were taught C is about light, but it's deeper. C is baked into Maxwell's equations, sure, yet it's also the conversion factor that keeps cause before effect in every inertial frame. If you let influences outrun C, you create race conditions. 2 observers disagree about which event happened first. That's fatal to any consistent computation. The cap on propagation speed is nature's way of preventing contradictory writes to the ledger. Everything clicked harder when I paired C with Margolus-Levitin. Picture a giant distributed system. The energy you allocate locally sets your tick rate. The spacetime fabric sets your message delay. That's exactly how we build reliable simulations. Accept a finite communication horizon, avoid speculative cross-node guesses that create contradictions, and reconcile when signals arrive. Relativity feels like that. Slower but stable beats fast and inconsistent. Let's get concrete with numbers you can feel. Take a lab-sized region, say a cubic meter, filled with air at room temperature. There's a finite thermal energy sloshing around. So there's a ceiling to how quickly that cubic meter can evolve into mutually distinguishable microstates. If you insisted on tracking every molecule's position and momentum with absurd precision in real time, the ops bill explodes. Even with all that energy, most of your ticks would be spent just keeping up, not doing anything useful. The universe avoids that waste by compressing dynamics into conserved quantities and effective variables. More on that next. But the reason it must is this budget: finite ops and finite reach. Now what about entanglement? The place where people think quantum tricks might cheat see. Here, that's what most people miss. Entanglement creates strong correlations, yes, but without a classical message, you can't control what your partner sees. Signaling still requires a distinguishable change at the receiver, and that change must be delivered by something that travels no faster than c. In other words, entanglement gives you shared random bits. It doesn't give you superluminal bandwidth. The budget holds. Local energy sets your tick rate, c sets your delivery window. Micro story. I once helped debug a distributed simulation of a plasma. We tried a predictive push, so nodes would guess neighbors' next states to hide latency. It screamed until two guesses collided. Different parts of the grid believed different histories, and the run blew up. We fixed it by enforcing a finite light cone. No update finalized outside its causal neighborhood until messages arrived. Slower on paper, but now the simulation never contradicted itself. Relativity reads like that fix written into the fabric. Credibility check. The Margolus-Levitin bound comes from Anil Margolus and Lev Levitin's 1998 result. The minimum time to evolve to an orthogonal state is at least h/4e for time-independent Hamiltonians. Stated as a rate, that's 2 EH operations per second. Combine that with c from special relativity, Einstein's 1905 framework baked into Maxwell's equations and every relativistic field theory, and you've got a principled ceiling on local clock and global reach. These aren't speculative, they're standard results. Here's the practical implication for you. Every high-speed thing you care about negotiates with these caps. Cameras chase higher frame rates by pouring in energy and reducing noise, but they hit shot noise and heat. Fiber links push bits close to Shannon capacity, but signal shaping and repeaters still respect C. Quantum computers can do exotic parallelism in Hilbert space. Yet their logical gate rates are limited by control energy, coherence, and readout. Again, ops per joule and no faster than light fanout. The simple version: energy buys you clock, C limits your reach per tick. That turns speed of light from mysticism into middleware. And once your clock and reach are capped, brute forcing detail everywhere is impossible. The only winning move is to compress, store rules, conserve what you can, and update only what matters. That's why symmetry and conservation aren't just elegant, they're cheap. Compression everywhere, symmetry, conservation, Noether. Here's what most people miss. Once your clock rate and reach are capped, the cheapest move isn't to track everything, it's to shrink the description. And the master tool for shrinking is symmetry. Okay, so basically, a symmetry is a change you can make to a system that doesn't change the facts you care about. Rotate a perfect sphere, same sphere. Slide a crystal by one lattice spacing, same crystal. If the description doesn't change, you don't pay to store new data. You store the rule that generates copies. That's compression. Everything clicked for me when I connected that idea to Emmy Noether's 1918 theorem. She proved that every continuous symmetry of the action produces a conservation law. Time translation symmetry. Physics works the same today and tomorrow, yields energy conservation. Space translation symmetry. Same rules here and there, gives momentum conservation. Rotation symmetry. No preferred direction, gives angular momentum conservation. Those conserved quantities are like checksums. You don't track every microscopic shuffle. You keep a few invariants that constrain the entire evolution. Lossless compression for dynamics. Think of conservation as caching. If total energy can't change, you don't recompute that sum every tick. You carry one number forward and let it vet every interaction. Momentum conservation nails collision outcomes without simulating each atom in both objects. Angular momentum saves you from tracking the torque of a trillion tiny forces if the net is zero. You're not ignoring reality. You're reusing structure to avoid redundant bookkeeping. Micro story. I once tried to describe wallpaper to a friend tile by tile. She rolled her eyes. Give me one patch and the rule repeat. Exactly. The tear in the wallpaper. That's the real data. Physics works the same. Symmetry compresses the regularities so the deviations, the interesting parts pop. Here's the weird part. We treat elegant laws like an aesthetic win, but elegance is thrift in disguise. Maxwell's equations compress mountains of electromagnetic phenomena into 4 lines because of deep symmetries: Lorentz invariance and gauge invariance. The standard model looks busy, but compared to listing every scattering outcome, it's a tiny program generating huge behavior. General relativity does the same trick. Demand diffeomorphism invariance, no privileged coordinate labels, and geometry becomes dynamics with a minimal rulebook. Gauge symmetry is economy at work. Multiple mathematical descriptions correspond to the same physical state, so you only store equivalence classes, the invariant content, not the redundant gauge choices. Lorentz symmetry lets you compress all inertial perspectives into one invariant interval. You don't keep a separate universe for every velocity. Renormalization adds ruthless budget discipline. As you coarse grain, averaging over short distance wiggles, most couplings fade. Only a handful of relevant parameters survive to control large-scale behavior. Translation: ignore the expensive microdetail unless your resolution demands it. Okay, so how does this save compute under the caps we just set? Local rules plus conservation laws turn evolution into an ON algorithm. Each site talks to neighbors, updates with constraints, and passes on a few numbers that must hold. You don't broadcast global state every tick. And because C forbids instant coordination, these invariants act like low-cost messages that keep distant regions compatible without heavy synchronization. It's distributed consistency for almost free. Symmetry breaking looks like a failure until you do the accounting. When a magnet cools and picks a direction, it stores a bit, the chosen orientation. That local spin buys macro-level compression. The messy microscopic spins reduce to an order parameter and a few soft goldstone modes. You pay for the choice, then amortize the savings across the whole material. Nature spends bits where they create robust, compressible structure. Even chaos gets compressed statistically. You can't predict every swirl in a turbulent flow, but the distribution follows scaling laws. Thermodynamics is the ultimate compression engine. It reduces astronomical microstates to temperature, pressure, and a few relations because permutation symmetry over microconfigurations, plus conservation pins down the macrostates. That's deliberate lossiness tuned to your resolution. Let's get practical. Particle colliders aren't drowning in raw coordinates. They lean on symmetries to slash the search space. Use translational symmetry to define the center of mass frame, rotational symmetry to average over angles, and conservation to reconstruct invisible particles from missing momentum. The expensive computation, the brute force microstate tracking, never happens because the invariants steer you straight to the anomalies. Credibility markers. Noether's theorem 1918 is standard. Gauge symmetry and Lorentz invariance underpin Maxwell, quantum electrodynamics, and the Standard Model. Renormalization and the renormalization group, Wilson's 197's revolution, explain universality at critical points. None of this is fringe. It's the backbone of modern physics. Here's the counterintuitive payoff for you. You toss a ball, and your 20-watt brain predicts the arc because symmetry and conservation annihilate irrelevant detail. You look at the night sky, and cosmic isotropy compresses the view to a uniform backdrop with tiny deviations, the data-rich bits that teach us about the early universe. Your cognition rides on the same economy: store rules, flag surprises. So the pattern's clear. With a finite ops budget and a finite speed of influence, the universe can't update every pixel at infinite fidelity. It survives by compressing symmetry, caching conservation, and pushing detail to the margins. But compression alone isn't enough. You still need a policy for when to commit bits. That's where quantum measurement turns thrift into a render strategy. Reality renders at need, quantum measurement. If the universe can't afford to update every pixel every tick, it waits to commit until something forces its hand. That's the clean way to read quantum measurement without the fog. Okay, so basically, a quantum state is a compact to-do list of possibilities. It evolves reversibly and cheaply under Schrödinger's equation. No heat, no paid deletes. The bill shows up only when an interaction leaves a durable record that says, "This happened." That commit is where energy and entropy move. Think of the wave function as deferred computation. Amplitudes carry options. Phases carry how options will interfere. Until a record exists, the system keeps alternatives alive in sewer position because it's cheaper than finalizing. The moment a measuring device couples and amplifies a microscopic difference into a macroscopic mark, an ionized trail, a voltage pulse, a pointer deflection, you've written a bit that would cost kT ln2 to erase at the device's temperature. That's Landauer walking into quantum mechanics, committing an outcome rights to memory. Erasing that memory has a minimum heat price. Here's what most people miss. The observer can be a warm table, a dust grain, or a camera. Mine not required. What matters is decoherence. The system gets entangled with many uncontrolled degrees of freedom, and the relative phases that enabled interference disperse into the environment. In practice, you can't gather them back. The environment selects a stable, pointer basis of states that resist further scrambling, exactly the ones that look classical to us. No neon, collapse in the equations, just unitary evolution making records irreversibly readable. Everything clicked for me with delayed choice experiments. In John Wheeler's setup, you decide at the last moment whether to close an interferometer. Keep it closed and you see fringes. No which path record exists, so the cheap superposition survives. Open it so which path information becomes available, and the fringes vanish.